All right, welcome to the second part of Unit 2 in pre-algebra. And we're talking about rational expressions now. We did the integers class, which we knew was positive and negative numbers. Now we're talking about rational numbers. So we're going to understand, first of all, what does it mean to be a rational number versus the opposite, an irrational one. All right? And then we're going to go through, first of all, some things that we need to have as prerequisite skills before we start adding, subtracting, multiplying, and dividing rational numbers, aka fractions and decimals. Let's see what's going on here. How come I can't? There we go. All right, so first of all, when you think about the fraction, and hopefully you know what a fraction is, the fraction 1/2, what is the mental model that you come up with when you think about 1/2? So think about, okay, the fraction 1/2. What do you picture in your mind when you do that? Okay, so when I typically go around the class and I ask this, there's some different ways that people do think about this. Okay, some people might think about pizzas or apple pies or something like that, and that would be simply like an area of one being cut in half. So if I draw a pizza pie, that would be simply half of the pizza pie on that side and half of the pizza pie on the other side. Other people might think about a number line and the space that is exactly between 0 and 1, or you can conceptualize a ruler is at the 1/2 mark. Okay, exactly between 0 and 1 is 1/2. Other people, their mental model might be something that has to do with probability, and you'd be selecting 1 out of 2, and 1 out of 2, okay, is also the equivalent fraction 0.5 of the population, right? Exactly half of a larger group, so 3 out of 6 is also an equivalent fraction for 1/2. Or you might think about 1/2 simply as an arithmetic process, 1 being divided by 2. And when you do that, 1 being divided by 2, 2 goes into 1 0 times, bring down the decimal, but it does go into 10 5 times, so that makes the decimal 0.5. You know, and that's a little elementary, but it's good to have a mental model and some differing mental models of how fractions work and how they look and how they feel. What about an improper fraction, 3/2? What does that look like? Well, you might have the actual three, let's say that these were pizzas, they're hexagonal pizzas, which I'm not sure that I've ever seen before. But still, you have three whole objects being cut in two. Well, if you had three pizzas to share amongst two people, each person would get 1 1/2 pizzas. And that is called a mixed number. The one whole plus the extra 1/2 making a mixed number. Or let's say if I just drew a line right across, right through these three pizzas, hexagonal pizzas, of course, that is three half objects. So if I'm cutting it in two, I've got a half here, a half on the top, and then another half on the top, making the improper fraction 3/2. And it's called improper because the numerator is greater than the denominator of that fraction. Okay? And these are both what we'll call rational expressions. And what the root word in rational is ratio. And that means a rational number is one that can be a fraction. We'll talk more about that. One that can be a fraction would be a rational number. There are some numbers that can't be represented with fractions. They can't be represented as a ratio of two whole numbers, or two integers, I should probably say. Okay? What about 5/8? Well, you could say, okay, I've got 5 whole pizzas being split amongst 8 people. Okay, so I've got 5 whole objects being split 8 ways, and I've got these wonky colors. And you see that each person, if designated by a color, does not quite get one whole pizza. They are getting a little over half of a pizza, and that decimal, that portion of a pizza would be 0.625. That's what 5 divided by 8 is. Each person would get 0.625 of a pizza, or 62.5% of a pizza, if you want to think about it in terms of percentages. Okay? But you could also think about the fraction 5/8 as being, okay, you've got a pizza that is cut into eighths, that is cut into 8 slices. So now these are octagonal pizzas, of course. Very nice for cutting into 8. very tough to make a octagonal pizza with actual real dough, I would assume, though. Anyway, um, and so you're cut into eighths, and you get five of them. And five of means times. 5 times 1/8 is equal to 5/8. So this would be the proper fraction, 5/8. This would be the equivalent decimal. 5 being divided by 8 is 0.625 in decimal land. Okay? So each rational number will still have a equivalent decimal as well, right? So you could be represented as a fraction, or you could represent it as a decimal, and they do have the same exact value. If you notice, I can just draw in those 1, 2, 3, 4, 5 slices, and you can see that 0.625 of a whole is equal to 5/8. Okay? Let's check out making a mental model by measuring a fraction on a ruler. Okay, so if I have to go to inches and I'm measuring 2 3/4 inches, okay, I have to note the quarter lines. There's a quarter line, another quarter, and then I'm back at 1, another quarter, another quarter, another quarter, and back at 2, another quarter, another quarter, another quarter, and I'm at 3, etc. Okay, so these are split into, inches are split into halves, quarters, eighths, and in this particular case, 16ths. Some of them even have 30 seconds on them. But inches in the good old US of A are split into halves, quarters, eighths, 1/16, dot, dot, dot. And that does continue. You can even have a more specific one, 30 seconds. So if I need to measure 2 3/4 inches, I would, let me get a highlighter for this job. Get a highlighter. I would start at 0, and I would go, okay, there's 1 inch, there's 2 inches, and then 1, 2, 3/4. And my highlighted space there is indicative of 2 3/4 inches. Okay? Let me try to do the same thing for centimeters. And centimeters, if you notice, is the metric system, and it's smaller. Okay? So it's like, let me give my highlighter out again. And there's 1 hole, there's 2 holes, and then, where are the quarter marks on this? And I've run into a bit of a conundrum. I can estimate where about 2 3/4 would be, somewhere around there. Okay, but it's actually a little more difficult to measure 2 3/4 centimeters because I don't have a notch that's small enough. If you notice, centimeters are divided into tenths. Right? So it would probably make more sense to represent any distance with a centimeter as a value of tenths or a decimal even. But 2 3/4, I might have to consider that that's 2.75, and that should be in between. 2.75 is greater than 2.7, but 2.75 is less than 2.8. So it's right there on that centimeter number line. Right? Just something to think about, okay? 4 does not go into 10, so therefore, if I have to measure 3/4, I'm going to have to either find a more specific metric system ruler, which that would be really, really small if you have to go below a millimeter. But anyway, what is the difference between these two types of measurements? Well, first of all, centimeters is the metric system, and it is smaller. And inches is the customary United States system. And inches are larger. There's about 2.5 centimeters, not exactly 2.51 something, I believe, inches per, or sorry, 2.5 centimeters per inch, and they just get divvied up in different ways, right? Converting a mixed number back into an improper fraction and vice versa. Let's check this out. So if I have 17/8, if I think about those 8 slices of pizzas that I had from that previous example on my octagonal pizzas that are very tough to make, I've got 17 of those slices. How many pizzas, how many whole pizzas have I eaten? Well, let's see, 8 goes into 17, a whole 2 times. But there's a remainder. 2 times 8 is not 17, it is 16. There's a remainder of 1. So I'm going to put that remainder of 1 on top of the original divisor. All right? 2 remainder 1 is 2 1/8. 2 whole pizzas and 1 extra left over. Okay? No big deal. 2 1/8 going back to 17/8, you could say, well, 2 times 8 is 16 plus the extra 1 is 17, and they both work out to the same exact number. But what about when there's a negative here? Does that change anything? Not really. 5 goes into negative 49, negative 9 times. In this case, I'll have a remainder. 9 times 5 is 45. I'm going to have a remainder of 4. So in this case, I have my mixed number is negative 9 and 4/5. Just make sure that if you have a negative numerator or if there's a negative sign maybe out in front of the fraction, that you account for that when you put in your final mixed number answer. Okay? So go ahead and convert these improper fractions to mixed numbers. Pause the video, and I'll do the same. Let's see if we get the same exact mixed numbers. All right, so I've gone ahead and filled out 9/4 converted to 2 and 1/4. So I went and measured that on the ruler, and since it was in quarters, I used inches, and I put 9/4 at the 2 1/4 mark. And 11/8 is 1 whole and 3/8, so I put it as over 1 and counted eighths, 1, 2, 3, and I put 11/8 there. And 23/10. 23/10. Well, since my inches are not split up into tenths, I found it better to use the centimeter mark, the centimeter number line, if you will, to say that 23/10 is 2 3/10. So I went 2 wholes and then it counted extra 1, 2, 3/10 on my centimeter mark. Hopefully you got those mixed numbers too. Okay. Now let's go the other way. 5 1/2 and negative 1/4. Well, like I kind of alluded to in the past slides, 5 1/2. Okay, well, how does that convert to an improper fraction if necessary? Well, what we're going to have to do is we're going to, as this note says, multiply the denominator and the whole number. Then add the extra numerator to your product and put that over the original denominator. So let's go ahead and do that. So 5 times 2 is 10. We're going to add the extra 1, and that'll give me 10 plus 1 is 11. And then I'm going to put that over the original denominator. So this should have come out to 11/2 as a improper fraction. Okay? And FYI, if there is a negative sign and you're doing this process, we're just going to simply, as a cheat hack, we're just going to simply ignore that negative sign for now and then slap it on at the end. And I'm going to get too complicated of why we do that, but let's just follow that rule for now. 11 times 4 is 44, plus the extra 1 is 45. And this will be 45/2, but don't forget that the value was negative to start from. You could put that negative sign up top. You could put it out front. It doesn't really matter. The whole value of negative 45/2 will be correct. Now, people ask, okay, well, Mr. Cummings, if I take the negative sign into account, negative 11 times 4 is negative 44. And if I add 1 to that, isn't that negative 43/2? Why is it not that? Well, in this case, this negative sign is indicating that not only is the whole number negative, the 1/4 is negative as well. So if it's negative 11 plus an extra negative 1/4, it doesn't look like this. It's not negative 44 plus 1. It's negative 44 plus another negative 1. Okay? Probably went into that a little too deep, but in this case, the negative 45/2 converts to our correct mixed number that we need. Turn these mixed numbers into improper fractions. Go ahead. Let's see if we get the same answers. All right, check to see. Did you get 33/8? Did you get 5/2? That's 2 1/2. Did you get 1 2/5, which is equivalent to 7/5? And did you get negative 3 2/3, which is equivalent to negative 11/3? Okay? Come ask me questions if you did not get any of those mixed numbers, right? So making equivalent fractions is another essential skill that we kind of need as a prerequisite going into this unit. So if I have the fraction 2/4, I can either reduce common factors out of 2/4, or I can multiply by common factors to make this even, I guess, less simple of an expression. But 2/4, let's go ahead and divide by a common factor of 2, right? 2 goes into 2 and 4 goes into 2, so I can reduce this. This is called reducing it to 1/2. Or you can choose to multiply, let's say, by any common number on the top and the bottom, as long as that number is the same. This could also be 6/12, right? And that is not reduced. You could also multiply by 1,000 if you wanted to make this 1,000 2,000ths. These are all equivalent fractions. There's an infinite amount of those, right? But as long as you multiply, the ratio has the same factor on the top. You multiply the same factor on the top of the ratio as you do on the bottom. The numerator and the denominator get the same factor. You're good to go. Let's go ahead. Let's first and foremost reduce 6/8 to its simplest form. If you see this arrow pointing down across a fraction, like your calculator says, that means it can be simplified or reduced, right? 6/8 reduces common factors down to 3/4. That would be the simplest version of that rational number. But you could also make this 60/80ths if you wish. You could also make this 15/20ths. These are all equivalent fractions. 10/5. 10/5. So we've got an improper fraction in this particular case. So 10/5. These ones get divided by 2 as well. Or sorry, these do not get divided by 2. They get divided by 5. Divide by 5 on top, divide by 5 on bottom, and we have 2/1. And any number over 1 being divided by 1 is just itself. So in simplest form, that fraction could be just simply 2. But if you wanted to, you could make it 100/50 as well, and it's still equivalent. What about 1/3? 1/3. Well, 1/3 is already simplified, so let's go ahead and just make a couple equivalents. I'm going to maybe multiply by 3 on top, 3 on the bottom, make it 3/9, maybe 10 on top, make it 10, and then over 30. Okay, something like that. All right, so equivalent fractions can go on forever, but that's still an essential skill. What about taking the decimal version of a rational number and turning it into a fraction? Well, for ones that stop, we have a longer, more extensive process for fractions that repeat, and we'll get into that as an extension sometime later. But for decimals that stop, let's just go ahead and just read the decimal, not like a calculator. You wouldn't read 1.1. Let's read 1 1/10. And let's actually just go ahead and write that fraction, 1 1/10. So you do have to be aware of your place value. If you know that 1 1, this is the tenths. This next decimal would be the 100ths. The next decimal would be the thousandths. The next decimal is the 10,000ths. We just keep adding zeros here. And this next decimal would be the 1/100,000th. Okay, etc. So in this one, it lands not in the tenths place, but in the hundredths place. So we say that that is 23/100ths. And that cannot be reduced. So I found my equivalent fraction, 23/100ths. And this one is 0.782, which, if read not like a calculator but correctly, is 782 thousandths. So let's go ahead and write 782 out of 1,000, or over 1,000. And this one actually can be reduced by a factor of 2. And I know the bottom's going to be 500. Gonna have to do some mental math here. 391. Check me on that. If I am not correct, come up and flex on me and say that I am not correct in that particular 391. I think that makes sense to me, though. Okay. Now, comparing fractions. 9 out of 13, which is greater and which is smaller, okay? So we could actually just divide these out with a calculator and find their decimal version and see which one is greater and which one is lesser. But let's actually consider something a little bit different. Let's compare these two numbers using what's called a common denominator. So 13 and 11ths can't be readily compared because the slices of pizza aren't the same size. They aren't the same size. So let's make a common denominator here. If I multiply 13 times 11, I find a common multiple between them, 143. 13 goes into 143 11 times. 11 goes into 143 13 times. So what I multiply by the top, I must multiply by the bottom. So let's go ahead and just multiply the 9 times the 11 that got multiplied on the bottom as well. And the 7 times the 13 that got multiplied on the bottom of its fraction. And on its top, I should have 91. And you can see that 99 143 is greater than 91 143 is. And there's a little cheat hack that you can use. You can just diagonally multiply. If you like, 13 times 7 is 91. And 11 times 9 is 99. And it assumes that there must be a common denominator there. Okay? Now, instead of 18 and 24, instead of making a common denominator by multiplying these two values together, 18 times 24, they're kind of big. It might be prudent, it might be wise for me to consider what is called the LCD. Okay, that is the lowest common denominator. So what is the lowest number that 24 and 18 both go into? Well, I know what it is, but if you'd have to think about the multiples of 18. It got 18 times 2 is 36, and then times 3, 18 times 3 is 54, and then times 4 is 72, okay? And then 18 times 5 is 90, okay, etc. Multiples go on forever. My multiples of 24 are 24, 48, 72, 96, etc. My mental math is slow and struggling this morning. I apologize for that. Okay, but if you see, 72 is the first time that they have a common multiple. So 72 is a common multiple here, right? So 24 goes into 72 3 times, and 18 goes into 72 4 times. So let's multiply the same number on the top. That is 52. 13 times 4 is 52. And 17 times 3 is 51. So in this particular case, I have just by 1/72 of a number, 13 out of 18 is a bigger number than 17 out of 24 is. So if you think about, like, we're shooting hoops, and one person made 13 out of 18 shots from the free throw line, and another person made 17 out of 24 shots. Who is shooting better? This person made more, but they took more. This person made less, but they took less. And you could say, well, they're both shooting about the same, and that would be true. But you could also brag that you are 1/72 of a value better if you made 13 out of 18 than you made 17 out of 24. Okay, so there you have it. We walked through some essential skills. So what is a rational number? I want you to just highlight this. Rational numbers can be represented as a fraction. That is a ratio between two integers in the infinite integer universe. So for example, the fraction 2/3 is rational because 2 is an integer and 3 is an integer. The fraction negative 281 over 5,000 is also a rational number because that negative 281 is an integer and 5,000 is an integer. They have no fraction or decimal parts in them. So another way to think about it, since we got our rulers, is their value can be measured on a ruler, depending on how you divided up the sections of that ruler. So if you have a fraction like 1/3 or a fraction like 1/4, their decimals will either stop, like 1/4 does, 1/4 is 0.25, or they'll repeat like 1/3 does, 0.3 repeating, goes on forever and ever and ever. Okay? So 1/3, 1/7, ninths, elevenths, They all have repeating decimals because those numbers do not go into 10, they don't go into 100, they don't go into 1,000, etc. Right? So the decimal versions of a rational number will stop. But you can have an irrational number. And the most famous irrational number that you guys have used is pi, obviously. It's 3.14159 dot dot dot. Goes on forever, and it has no pattern and no repeating. No end, sorry. No pattern and no end. Okay? So let's see. Square root of 2 is also irrational, 1.41 something. The square root of any imperfect square, square root of 10, is irrational, right? It doesn't have a whole number um, or a stopping decimal or a repeating decimal that could represent it. It's really hard to measure the square root of 10 on a ruler. But let's put in some rational numbers. So we talk about natural numbers like 1, 2, 3, and 4 are natural, and they are rational. I could represent 2 as 2 over 1. Okay? Whole numbers. Well, all of these numbers are whole. The only whole number that's not a natural number would be 0. Integers, -20, -5, -1,000. These are all, okay, if you notice, there's in the integer set, you have positive numbers, natural numbers. You have whole numbers, 0, and you have the negative values. We'll have the opposite of 4, -4 in here. The opposite of 1 is -1 in here. But then what it means to be rational is you can be a fraction. You can be a fraction. So let's throw some fractions and decimals in here that could be fractions. So for example, let's go the simplest fraction, 1/2, 1/10, why not? 0.22. Well, 0.22 is 22/100ths, which converts to 11/50ths. It can be a fraction. How about 0.3 repeating itself? Is 1/3. It can be a fraction. So any number that could be a fraction is considered rational, and any number that cannot be turned into a fraction is irrational. But these are still part of what we call the real number set. Hope that helps introduce this particular unit, and we have some prerequisite skills to draw upon moving forward. Have a nice day, guys, and don't forget to like and subscribe.